Okay, let's dive right into this explainer. We're looking at what is arguably the most ubiquitous, yet completely bizarre substance on Earth. Yeah, water. I mean, it's sitting right there in your glass, it's falling from the sky, it makes up the vast majority of your very own body. We interact with it every single day, so, it's incredibly easy to just brush it off as normal. But as we're about to see, normal is the absolute last word you should ever use to describe H2O.
Just take a second to wrap your head around this number. 1.38 billion cubic kilometers. That is the total volume of water on Earth. It literally coats our planet, and a whopping 97.39% of that is locked up right in our oceans. So, it's the most abundant substance on Earth's surface, right? But here's the thing. Abundance often masks just how unbelievably strange something really is.
We totally take it for granted, because it's literally everywhere. Our brains just kind of wire themselves to think water sets the standard for how liquids should behave. But what if everything we know about this liquid is just one giant anomaly? We really have to ask ourselves if this seemingly boring everyday substance is actually a total cosmic oddball. Because honestly, when you compare water to other similar chemical compounds, it becomes glaringly obvious that water is just continuously breaking the rules of physics and chemistry.
Section 1. The architecture of H2O. Let's see how this oddball behavior builds directly from water's microscopic structure.
So, the absolutely crucial point here is that the oxygen atom has these lone electron pairs that just need space. And they force the hydrogen atoms into this very specific bent shape, exactly 104.45 degrees. Now, because oxygen is more electronegative, which basically means it's a massive electron hog, it pulls electrons towards itself. This creates a highly polar molecule. So you've got a negative end and a positive end. And this specific structure is what allows water molecules to magnetically attract their neighbors, forming what we call hydrogen bonds. Now, these bonds are incredibly dynamic. I mean, they break and reform at timescales faster than 200 femtoseconds. That is mind-bogglingly fast. But collectively, they're strong enough to completely alter how the entire molecule behaves. This comparison really hits the nail on the head when showing how strange water is. Think about hydrogen sulfide, H2S. Sulfur sits right below oxygen on the periodic table, and hydrogen sulfide has almost twice the molar mass of water. So, following standard chemical logic, water should absolutely be a gas at room temperature, just like H2S. But it's not. Water's powerful hydrogen bonds practically lock it into a liquid phase under standard conditions. Literally, without that bent architecture, there would be no liquid oceans on Earth. None.
Moving into Section 2, a physical rule breaker. Stepping up from the molecular level, let's explore how these tiny bonds cause water to just blatantly ignore standard physical rules.
Think about what normally happens when things get cold. Most liquids shrink, right? They become denser as they freeze into a solid. But water is a total rebel. As it cools, it actually hits its maximum density at exactly 3.98 degrees Celsius. And when it drops below that temperature and starts freezing into regular hexagonal ice, those hydrogen bonds kick in and force the molecules into this wide open lattice structure. The result of that? Water undergoes negative thermal expansion. It actually expands and becomes about 9% less dense.
So why does this matter? Well, if water acted like a normal liquid, ice would sink. In the winter, surface cooling would trigger convective mixing, and our lakes and oceans would literally freeze solid from the bottom up. Everything inside would die. Game over. But because ice is 9% less dense, it floats, and that frozen surface layer acts like a giant thermal blanket for the water below. This means deep lakes can maintain a constant bottom temperature around 4 degrees Celsius all year long. Aquatic life survives winter simply because water refuses to act normally.
Furthermore, water's specific heat capacity is off the charts. We're talking 4184 joules per kilogram Kelvin. It takes a massive amount of energy to change its temperature, mostly because you have to break through all those hydrogen bonds first. And what does this mean for us? It means our oceans act as a colossal thermal shock absorber for the entire planet. They buffer these extreme fluctuations in temperature and basically moderate Earth's entire climate. I mean, without this crazy high heat capacity, Earth's surface would experience wild, completely unlivable temperature swings.
Let's scale this up and see how it builds into even larger earthly systems. There's this amazing step-by-step process called brine rejection, which happens when ocean water freezes. Now, because seawater contains salt, its freezing point actually drops to negative 1.9 degrees Celsius. When the surface does freeze, the ice that forms is essentially pure, salt-free water. All that salt just gets left behind in the liquid, making the water right below the ice incredibly salty and super dense.
So this cold, heavy brine sinks straight toward the ocean floor. And that exact sinking motion, that is the literal engine driving our global thermohaline circulation, those massive ocean currents that transport heat and nutrients all around the globe.
Moving on to Section 3, the chemical chameleon. Let's shift gears from physics over to chemistry, where water's polar architecture makes it this relentless, highly adaptable chemical chameleon.
This hydrogen bonding network gives water some seriously bizarre biological superpowers. Because of its strong cohesive forces, meaning water molecules just absolutely love sticking to each other, it generates an incredibly high surface tension. We're talking 71.99 millinewtons per meter. That is exactly why certain insects can literally walk across a pond's surface. Then you combine that cohesion with adhesion, which is water's ability to stick to other surfaces, and you get capillary action. This is the magic mechanism that allows giant trees to totally defy gravity and pull moisture hundreds of meters up into the sky. And on top of all that, water is amphoteric, meaning depending on what it reacts with, it can actually play the role of either an acid or a base. Talk about versatile.
You've probably heard water called the universal solvent, right? That's due to its high dielectric constant, which is just a fancy way of describing its ability to easily neutralize and pull apart charged molecules. When you drop regular table salt into water, the water molecules basically swarm the salt. They tear apart the sodium and chloride ions and just carry them away in solution. We call these hydrophilic, or water-loving, substances. But then you have nonpolar substances, like fats and oils, which are hydrophobic. The interesting thing here is that water doesn't actively repel them. It's just that these nonpolar molecules can't overcome water's intense desire to hydrogen bond with itself. So the water molecules stick together and they force the fats and oils to clump up and stay completely separate.
Okay, Section 4, water in the cosmos. Let's zoom way out to the cosmic scale to see how this molecule behaves beyond our own planet.
So get this, water is actually the third most abundant molecule in the entire universe, sitting just behind molecular hydrogen and carbon monoxide. But here's the catch, not all water is identically built. The oxygen and hydrogen atoms inside water actually come in different isotopic flavors, almost like slightly different versions of the same building blocks. Looking just at the oxygen, 99.76% of water uses the standard 16O isotope, but there are these tiny fractions that use 18O and 17O instead.
And things get even stranger when we look at the hydrogen atoms. Most water uses standard hydrogen, which is called protium, but occasionally water contains deuterium, a heavier hydrogen isotope that packs an extra neutron. When that happens, it forms what we call heavy water, or D2O. Now, because deuterium is quite literally twice as heavy as protium, this heavy water has a higher density, a totally different boiling point, and it interacts very differently with biological systems. In fact, if an animal were to consume heavy water in large amounts, it actually impairs kidney and nervous system functions. It can literally be toxic.
Now, while Earth feels like this massive aquatic world to us, here is a crazy fact. By mass, our planet is only 0.0000023% water. We are actually quite dry in the grand scheme of things. To find the real water worlds, you have to look way out, beyond the solar system's frost line. Out there, the sun's radiation is just too weak to vaporize ice. Compare our Earth to bodies out in that deep freeze, like Saturn's moon Tethys, for example. Tethys isn't just covered in a thin layer of water, it's almost entirely constructed of water ice, the whole shebang. From deep space all the way back down to our deepest oceans, it really all comes back to biology. Ultimately, this rebel chemical's unique ability to dissolve nutrients, form complex hydration structures, buffer global temperatures, and provide the perfect medium for cellular reactions, well, it truly earns it the title, the solvent of life. Basically, every single biochemical process that keeps you breathing and moving right now relies entirely on the incredibly precise, totally anomalous behaviors of this one specific molecule.
So, the very next time you drink a simple glass of water, I really want you to ask yourself a somewhat unsettling question. Are we just incredibly lucky beneficiaries of a molecule that simply refuses to play by the rules? Think about it. If water acted normally, Earth would be nothing but a barren, frozen rock. We exist precisely because water is an anomaly. Thanks for joining me on this explainer, and remember to always keep questioning the ordinary.